There are many different applications involving exponential and logarithmic functions. The first one that you see here gives you the price demand function. P is in terms of X, P is the price, X is the demand. It's in dollars. It's measuring the price that you can expect to charge for an item when you want to sell X units of this item. The interval this is defined over goes from 0 units all the way through 800 units. The first part of this problem wants us to find the revenue function in terms of X. We remember that to find revenue, we take price times quantity. Price is the variable P, quantity is the variable X. So when we put this together, we get the price function, 250 e to the negative 0.0025x times a quantity x. Or you can write this as 250x times e to the negative 0.0025x. This is my revenue function. And it's in terms of X. Part B says find the number of items you need to sell in order to optimize the revenue. The optimal revenue occurs at a peak of the revenue graph. So the way we're going to calculate where the revenue has a peak is by finding the first derivative. We will set that equal to 0, and we will solve for X. The first derivative of the revenue function involves the product rule. This is the first factor, and this is the second factor. We simplify this, it will look a little bit better. I'm going to factor out the common factor, which is 250 times e to the power negative 0.0025x. So that is the common factor that I brought out into the front. That leaves us with x times negative 0.0025 plus 1. Okay, so this is the simplified derivative of the revenue function. Next, we set this equal to 0. We solve for x. This is equal to 0 whenever the factor 1 minus 0.0025x is equal to 0. And so that is what we are going to solve for x. All right, so x equals 400 is what you get from that solution. So we are going to verify that the critical point we found as 400 is actually the absolute max. Verify that this is the absolute max. So to do that, we can use the extreme value theorem, because your function is defined from 0 to 800 on that closed interval. So we want to calculate R of 0, the revenue at 0. We want to calculate the revenue. We want to calculate the revenue at 800. We want to calculate the revenue at 400, and we should see that the revenue when x equals 400 gives us the largest revenue value. All right, so I'm plugging these values back into my revenue function, which is, I'll highlight it for you, it's right here. Okay, so we're going to plug in those values of x into that equation. The first one gives you 0. The next one, 250 times 800 times e to the negative 0.0025 times 800 gives you $27,067. Close enough. The next, when you plug in 400 to the revenue function in place of x, gives you a revenue equal to $36,788. Close enough. Dollars. And so that you can see that this is the max due to the extreme value theorem. All right, part C got eliminated. Let's see if I have it on paper. Part C would have said, I don't know what happened to it, but find the price that optimizes the revenue. So find the price that optimizes the revenue. Okay, so I'm not going to worry about getting that back. I must have deleted that. So to find the price, we remember that the price function given above in terms of the quantity was 250 e to the negative 0.0025x, all the way back to the beginning of this example. Okay, so this is the price function that we want to use in order to figure out what price we need to charge when we use the optimal quantity of 400 units. So we want to try to sell 400 units. In order to sell 400 units, the price we need to charge is equal to $91.97. Number 2, an epidemic spreads through a community so that T days after its outbreak, the number of people who have been infected is given by a logistic function of this form. The value of B, the value of C, the value of K, those are all constants. T is time after the outbreak. The total number of diagnosed coronavirus cases in China, T days after it began on January 22nd, approximately 2020, can be found using this function where the values are filled in for us. This data came from the source listed there on your paper, and the data was plotted and a logistic function regression curve was fit to that data, and that is the equation that we got. Sketch the graph of this function, use the window specified here. We're going to use the graph to figure out how many total diagnosed cases there were in China on February 1st, and so on and so forth. So I'm going to try to pull up the graphing calculator on my device and see if we can get this to show. Let's see. Bear with me. Okay, so hopefully you've got that on your graphing calculators. I looked for a TI calculator app on the App Store and I could not find one. So I'm doing the best I can to show you this using Desmos as my app. Okay, the window, let's see. The window we are specified to use for the x-axis goes from -3 to 60 on the x line, and the y-axis goes from -10,000 all the way to positive 95,000. Like I said, this is actually real data that I got from the source listed on your papers. This is a logistic function. You can see that it begins increasing I can't really mark on this, but it begins increasing at a fairly slow pace as you go across. And as you continue to increase, you notice that it goes up exponentially until you get to somewhere around t equals, let's see if I can paste this into a window. Give me 1 second. I don't think it's going to happen right now. I'll see if I can get better at the technology as our semester goes on. But this graph continues to increase. It looks exponential until around 20, t equals 20, and then it begins to level off after that. So I'm just going to try to sketch this over on our notes packet so that you can see what the graph looks like, and I'll be able to point to the different features once I get over there. Okay, so as we saw, the graph starts out at a slow increase, and then it looks to be as an exponential growth, but then it does level off. And that is the shape of a logistic model or a logistic function. This is, we're using t for time, and we're using f of t for how many cases there are of people who were diagnosed. Okay, so right around here is where 20 was. Okay, so slightly before that is where it changed the pace or how quickly it was going up, right? Okay, we're going to talk about that shortly. So that's not a great sketch, but hopefully you can see a better picture on your calculators. Use the graph to determine how many total diagnosed cases there were in China on February 1st. And so February 1st is how many days after the start of our function. So up here it tells you t is equal to 0, represents January 22nd. All right, so the first day later would be the 23rd. So let's see, there are 31 days in January, so let's count all the way to February 1st. How many days would that be after the 22nd? This looks like 10 days later. So February 1st is 10 days after the beginning. And so you're going to use your function on your calculators. You're going to hit the trace button. You're going to trace over on your graph until you get to, or actually once you've hit the trace button, type in the number 10 for me. Type in the number 10 and it's going to jump to that location on your graph exactly at 10. And when you jump there, you're going to get the output value, the y-coordinate, 13,000. F of 10 equals 13,529 cases. And that's how many cases there were 10 days after the start of the virus. Next, part C, use the graph to approximate the day when the total number of cases was increasing the fastest. Once again, you're asked to just find this approximation when the graph was going up at the quickest rate. Okay, so this graph is going up at the quickest rate right where I marked this point 16. That is actually the inflection point. So what this part C is asking you to find is the inflection point. The inflection point is this point of interest. happens when t is about 16. That's an approximation based on what my graph showed on the calculator. How could this answer be found using calculus? So that, remember, the inflection point tells you where the graph changes its curvature. So prior to t equals 16, this graph is going up at a very quick pace. And then after 16, it's still increasing, but it begins to level off. Like if you were to start drawing in tangent lines before 16, you would notice that they're increasing at a pretty quick pace. And then after 16, the tangent lines begin to become less steep. So describe how this answer could be obtained using calculus. The process, I don't have room to write it all out, but the process is going to say you want to find where the second derivative is equal to 0 and solve that for t. Solve for t. And that would give you the inflection point. This gives the inflection point. Okay? Part D, what will be the approximate maximum number of diagnosed cases? In other words, if you look at this graph, as time goes on towards the right, does this graph begin to level off and does not appear to grow much higher? And the answer is yes. Let me show you the more exact version using our Desmos graphing calculator app. It does look like this graph begins to level off as I scroll to the right and t gets bigger and bigger and bigger. Look at that. That red line looks like a flat horizontal line once you get out so far. In fact, check this out. If you were to graph the equation y equals, let's use 81,350, you're going to see that that is the horizontal line that your function in red gets closer and closer to, and it's never going to go at that rate, or sorry, not at that level or even higher. It stays below the horizontal line, 81,350, and therefore that is the maximum number of cases we can expect in the country. Okay? And the reason I know this is because I know how the logistic function works. It's going to be the numerator of your logistic function, which corresponds to the value that we called b. So up here, whoops, sorry about that. That is going to be this value, I guess I'll use orange. B tells you where this graph is going to stay below. Okay, and in this case, the value of b is 81,350. It's the upper limit to the number of diagnosed cases. So if you've been watching the news, you know about the coronavirus, and you may have even seen some of these types of graphs pop up on the news screen. So I wanted to pull out this information because it's relevant in our particular chapter to help you understand a little bit more of what the graph looks like. And so you can keep track of the graphs for the other countries. Since China was ahead, they were the start. That is where the virus initiated, was in China, and so therefore they're a few weeks ahead of the rest of the world in how this virus progressed through their country. So you can look at the other countries to see if they have appeared to have hit their inflection point, and then you can kind of approximate what that maximum number of diagnosed cases might look like.